Here we'll explain the idea of the critical angle at an interface and the idea of total internal reflection. And for this diagram, I'm going to draw the interface horizontally, and we'll say that to start with, your N on top will be 1, so the material is air, and then the medium on the bottom is water, 1.33. So we have the lower index on top, the higher index on the bottom. And if we go ahead and draw in a normal, anytime that we have an incident angle in the lower index medium, the light ray is going to bend toward the normal. So the angle of refraction must be smaller than the angle of incidence. And you can see that theoretically the largest possible angle of incidence that we could have would be 90 degrees. But even if that angle of incidence is 90 degrees, the angle of refraction, because it's going from low index to high index, is going to be smaller than 90 degrees. So when you're going from low index to high index, the angle of refraction is always going to be less than 90 degrees. Now if we say that the light is incident in the higher index medium, so it's going from the water to the air, this would be your incident angle. And when it goes into the lower index medium, it bends away from the normal. So here your theta prime is larger than theta. Your refracted angle is greater than the incident angle. And I'll also mention here, you remember that at an interface, some of the light is transmitted and refracted, but also some of it is reflected, and this angle of reflection is going to be equal to the angle of incidence. So in this case, some of the light is refracted and bent away from the normal, and then some of the light is reflected back into the water at that same angle of incidence. If we were to increase the angle of incidence, the angle of refraction would also increase and be greater than the angle of incidence. And if we increase it even more, we'll eventually get to a point, if this is our theta, the theta prime must be larger than that, and we would get to a point where the refracted angle is equal to 90 degrees. And this would only occur, it's only possible for this to occur, if the light is going from the high index medium to the low index medium. And in this case, that incident angle where that gives the refracted angle of 90 degrees, the incident angle we call the critical angle, and we label that theta c. And what that means is any angle greater than that would create total internal reflection. And the reflected angle would be equal to the incident angle. But none of the light would be transmitted or refracted on the other side. So I want you to keep in mind when you're looking at this that for each incident ray there's some of that light reflected, like we had drawn this one in to start with, which would be the reflected light from this incident ray. And as the angle of incidence increases, the percentage of light that is reflected is also increasing until you reach the critical angle where 100% of the light is reflected. And so you can also think that as the incident light increases, the amount of light that is transmitted is going to decrease. So again, the definition of the critical angle is the incident angle that gives us an emergent angle of 90 degrees, or I'm sorry, refracted angle of 90 degrees. So we can use Snell's law to help us determine the critical angle. And here, the incident angle is our critical angle. And the refracted angle is going to be 90 degrees. The sine of 90 degrees comes out to be 1. So you can actually simplify this to say that the sine of the critical angle is equal to n prime over n. So this secondary equation may or may not be one that you choose to memorize. You might prefer just to kind of think of it more conceptually along with the original Snell's law. Our example will find the critical angle at an interface between glass and air. Glass has an index in this problem of 1.50, and the air we know is 1. And remember that the critical angle is always referring to when we're going from the high index medium to the low index medium. So that means that the glass must be our n, and the air must be our n prime. And the definition of the critical angle is the incident angle that will give us an emergent or refracted angle of 90 degrees. So if we say n times the sine of theta c, our critical angle or incident angle, is equal to n prime times the sine of 90 degrees, which by definition would be our refracted angle. The sine of 90 degrees is 1, so this actually comes out sine of critical angle equals 1 over 1.50, and you can solve for theta c to find that it is 41.8 degrees. And if we want to draw that out to see what we're talking about, so if we had the glass here and the air here, drawing a normal, and if our incident angle is 41 degrees, 41.8 degrees, then the emergent angle would be right at 90 degrees. And if we had any incident ray with an angle of greater than 41.8 degrees, it would be completely reflected back into the glass. None of it would be transmitted or refracted into the air.